Hello, my name is Karenisa and I'm from Group 10 and these are my group members. These are the options that we have chosen. For the first option, we chose 1C, and in this question, we are to reverse engineer the code you see on the right side of the screen and create a flowchart to describe the steps. I'll explain the built-in function that we have used in the code and then later on determine the time complexity of the MI algorithm. So the purpose of the function is to find the MI of A modulus M, and if it exists. The semantics are N represents an integer, A represents the number for which we want to find the MI, M represents the modulus, MI represents the multiplicative inverse of A modulo M. If it exists, it will return as 1, otherwise it will remain 0. The built-in functions in Scilab that we have used in this code are GCD, which stands for greatest common divisor, and it takes two integers as input and returns the largest positive integer and divides both of them without leaving a remainder. And the other thing is modulo, and in this function it calculates by dividing one number by the other and then later on taking in the remainder. These are the steps in the flowchart. So it starts with initializing mi to 0. Then it checks the GCD of A and M. If it is 1, if it's not, then the MI does not exist and the function will return 0. Then the program will end. If the GCD is 1, it will iterate through the numbers from 1 to M minus 1. For each number n, it will check if A times by n modulus M equals to 1, and it will loop until the condition becomes true. And if it is true, it will set mi equals to n, and then it will break the loop, then return mi, and the program will end. And then the time complexity of mi algorithm is dependent on whether A and M are co-prime or share factors. When they are co-prime, the time complexity is big O notation M, indicating that the runtime grows linearly with the size of M. When they are share factors, it is O log minimum A and M, indicating that it grows logarithmically with the smaller of A and M. In all cases, the time complexity has a lower bound of omega M, meaning the algorithm's runtime is at least proportional to M. Thus, overall, the time complexity can be summarized as theta M or theta log minimum AM. And in simpler terms, the time complexity increases with the size of the input numbers. For small numbers, that is quicker, and for large numbers, it takes longer.
I'm Norhana Pintu Bujang, going to explain the assignment for option 2B. This option 2B shows the weight graph. To find the shortest part for this graph, we use the Dijkstra's algorithm from vertex to vertex H. First, we set A to 0 because the distance from A to A is 0, and every other distance we set to infinity. Then we start by calculating the distance to all unvisited neighbors of A. The distance from A to B is 2, and the distance from A to C is 2. And now we update the table on the right to mark the previous vertex. Then repeat the process to calculate the distance. B to D is 3 plus 2 is 5. B to F is 2 plus 2, 4. Then C to E is 5 plus 2 equal to 7. C to G is 3 plus 2 equal to 5. Lastly, G to H is 4 plus 5 equal to 9. So all the distance update to the table. Now we want to reconstruct the path from A to H. The first thing, we start from vertex H, and the shortest distance is 7 to vertex F. Next vertex D is the short distance is 2. Next is the distance is 4, which vertex C. Then 2 from vertex A. And now we have found a connection from A to H that has the length 15 and is the shortest path.
Assalamualaikum. I am Aina Carmila binti Hajong Umekrat, and today I will be presenting my group's minimum spanning tree solution. So for the first algorithm, Prim's algorithm, we start with node A, and we are connecting the node to neighboring nodes with the lowest weight. By repeating this step, we are making sure that we are not forming any cycles. And we keep on doing this until all of the nodes are connected. For our final solution, the cost is 20. Moving on, for Kruskal's algorithm, we start with all of the edges with the lowest weight, which in this case is 2. We continue based off which has the lower weight, and similarly to the previous algorithm that we have covered, we are making sure that we are excluding the edges that forms a cycle. For our final solution, the cost is also 20.
My name is Arjana Binti Arifin, and I'll be presenting the payoff metrics and optimal strategies. Player R has 9 black and 4 red cards, while player C has 2 black and 8 red cards. The rules of the game are that, if there are different colors, player R pays player C the sum of face value, and if the cards are the same color, player C pays player R the sum of face value. The payoff matrix represents the playouts for each combination of cards chosen by player R and C. If R chooses black and C chooses red, R pays C $9. If R chooses red and C chooses black, R pays C $4. If both choose black, C pays R $2. If both choose red, C pays R $8. As we can see from the table, it shows in each cell of the matrix, the first value represents the payoff for player R, and the second value represents the payoff for player C. Moving on to the optimal strategies, we can see the calculation for each expected payoff for each player according to the colors red and black. If player R chooses black, the expected payoff equals to 6.8, and if player R chooses red, the expected payoff equals to negative 6.8, and if player C chooses black, the expected payoff equals to 6.007, and if player C chooses red, the expected payoff equals to negative 3.847. To conclude, both players will choose a strategy that gives them the highest expected payoff. The optimal strategy for both players is to choose the color that maximizes their expected payoff given the properties of the opponent's choices. This means that player R will choose black with an expected payoff of $6.80, while player C will choose black with an expected payoff of $6.77. So the optimal strategy for player R and player C is choosing black cards. The value of the game remains negative $2.
Hi, my name is Najiba Binti Remli. I'll be continue to explain about the calculation for value of the game by comparing the maximum and minimax strategies of both players. It ascertains the value of the game representing the expected payoff for player R. It determined the value as negative $2. So the calculation will be value is equal to minimax payoff for player R minus minimax payoff for player C. So both players play optimally. Though the payoff matrix analysis and dominance analysis used to identify optimal strategies for player R and player C, it structured the selecting and best response of strategies of the strategic interaction. Then player R's optimal strategy leads to a payoff of $8, emphasizing strategic decision-making importance.